We've now spent a couple lessons talking about radical expressions and radical functions, how to simplify them, how to do algebra on them with the usual operations, and how to solve equations which contain them. In this lesson, I'd like to come back to the theme of visualizing the graphs of these functions, just as we've already done with a number of other functions like polynomial functions. Now, as with our other lessons on graphing, some graph paper would probably be good to have as we walk through these examples. You might also want a calculator just to calculate any roots that you want, just in case you're trying to plot some points and connect the dots between those points as we sketch these graphs. So let's get started with what is probably the most basic example we can as we're drawing the graphs of radical functions. Here's the example. Sketch the graph of f of x equals square root of x. Now, the first thing we should do is ask, what is the domain of the function f of x equals square root of x? Well, keep in mind that we're not allowed to have negative numbers under that square root symbol because we only want to have real number answers. And that means that we need to have x greater than or equal to 0 in this function. So the domain of this function is the set of all real numbers from 0 and including 0 up to infinity. Or, said a different way, it's the set of all real numbers that are not negative. Now, that's an important point to make because it means that the graph of this function will only exist in the right-hand side of the Cartesian plane, because that's where all of the non-negative values of x live. So if you imagine having the plane with the x-axis and the y-axis drawn, there will be none of the graph of f of x equals square root of x on the left-hand side of the y-axis. It'll only live on the right-hand side. Now, as a next step, let me suggest that we get a feeling for the graph just by plotting some points. This is always a good idea. If you're stuck when you're graphing, just plot a bunch of points and try to see if you can see what the graph looks like. So let's plug in a whole bunch of values of x and see what the y values look like, and then plot those points in the xy plane. First of all, f of 0 equals the square root of 0, which equals 0. So that's no problem. And f of 1, which is the square root of 1, is equal to 1. Now, I might try f of 2 or f of 3, but I don't know those square roots very well, and I'm allowed to pick which values of x we plug in, so I say we plug in 4 as our next value, and f of 4, which is the square root of 4, is equal to 2. That one's easy to plot. F of 9 equals the square root of 9, which is 3, and again, I've jumped to x equals 9, because it's a straightforward value to plug in. So I know that the point 9, 3 would be on the graph. And lastly, if I plugged in 16, which is also a perfect square, f of 16 is the square root of 16, which is 4. So on a piece of graph paper, you could draw your x-axis and your y-axis and then fill in the origin, 0, 0. We saw that in our calculations. And you can also fill in the points 1, 1, 4, 2, 9, 3, and 16, 4, because that was the information we found. The last one we calculated was f of 16 equals the square root of 16, which is 4. And remember, that point, 16, 4, really is on the graph. But don't get confused and swap the x and the y. The point 4, 16 is not on the graph, because the square root of 4 is not equal to 16. So it's important here that we remember which of the numbers were x values and which of them were y values. Don't switch the two. And let me just reiterate. Remember, you and I get to pick which values of x we're going to plug in. And I chose to plug in 0, 1, 4, 9, and 16 because they were going to make the function's y values nice and clean. I didn't want to plug in 2 or 3 or 5 or 7 for x, because those values would have forced me to find some very unenjoyable y values. I would have needed square root of 2 or square root of 3, square root of 5 or square root of 7. And those numbers weren't going to work out nicely on my piece of graph paper. So there's nothing wrong with plugging in things like 2 or 3, but the output values are not going to be pretty. So just kind of step back and think about which values you want to plug in, which will make your work just a little bit easier. Now, let me suggest that you plot those points if you haven't already, and now connect the dots between them just to see what's happening. You should be getting a graph which starts abruptly at the origin. Remember, there is no piece of this graph to the left of the origin. And then this graph seems to be traveling upwards in quadrant 1 in a very gently rising fashion. Now, why does the graph start abruptly at the origin? Remember, because x equals 0 is the smallest value of x that's in the domain of this function. So that's why it seems to start at the origin and sort of jump out of it, if you will, and move its way to the right. Now, here's the next question we should ask. What does the right-hand side of this graph look like? Sort of, what does the end of that graph do as it continues to travel in the positive x direction? Does it take off eventually, something like y equals x squared, and go to plus infinity in a very rapid way? Or does it level off under a sort of ceiling line, a horizontal line, what we might call a horizontal asymptote, so that it never gets above that horizontal line? Well, actually, the end of that graph doesn't do either of those things. It doesn't turn and take off quickly to plus infinity in the y direction, and it also doesn't level off in such a way that it can't get above a certain value. What really happens is this. It does go to plus infinity in the y direction, so it keeps going up and up and up and up as we get larger and larger values of x plugged in. But it does so quite slowly. Think about it for just a second. Let's plug in a few other values of x, and I'll try to convince you that this function continues to grow, but it does so in a very slow fashion. For example, what is the square root of 100? So imagine I'm plugging x equals 100 into the function. Well, the square root of 100 is just 10. So if you go 100 units to the right on the x-axis from the origin, you only go up 10 units in the y direction to get to that point. What about plugging in something like x equals 10,000? Well, I'm choosing that because it has a nice square root as well. Square root of 10,000 equals 100. So again, starting at the origin and going 10,000 units to the right, I end up only going up 100 units in the y direction. And lastly, if I look at x equals 1 million, and I take the square root of that, then the y value, or the f of x value for x equals 1 million, is going to be 1,000, because the square root of 1 million is 1,000. So as my x value gets all the way up to 1 million, I do go up higher than I was going before, but I only go up to 1,000. So the y values are definitely getting bigger, and they're going to continue to get bigger as the x values get bigger, but they're not getting big very quickly. So I notice a very gentle sloping that occurs with that graph as it moves from left to right. So the graph is going to keep going up. It will go to plus infinity, and it's going to go slowly. And that means that it's not being bound up or bumped by a horizontal asymptote. It's going to keep growing and keep growing forever. Now, that's the basic shape of the graph of y equals the square root of x. In fact, in general, that will be the basic shape of many of the graphs that will involve the square root of x function that we'll see in this lesson. Now, not all of them are going to look like this, but many of them will. So to help you see what I mean, let's move on to a second example and see what the shape of this graph looks like. Now, if you can remember how f of x equals x minus 3 squared would have its graph drawn in relationship to f of x equals x squared, you might even be able to do this example yourself. And if you can, just pause the video in just a moment, and you'll be able to work on it on your own before we come back together. Here's the example. Sketch the graph of f of x equals square root of x minus 3. Now, we know from previous conversations that we've had about graphing that the graph of this function, square root of x minus 3, should be very, very similar to the graph of square root of x, which is the graph that you and I were just looking at a few moments ago. What has changed when you go from square root of x to the square root of x minus 3? Well, we have changed the x part of square root of x to the quantity x minus 3. Now, when you just change the x part like that to x minus 3, it means that the graph moves either left or right 3 units. Do you remember which one it is? It's to the right. So the graph of square root of x minus 3 is the same as the graph of square root of x, except it's getting shifted 3 units to the right. And so that graph also has this nice sloping shape, but now it's coming out of the point 3, 0. Okay, let's look at a different type of graph of a radical function now. And I'm going to ask you again, can you try to graph this one on your own? It's going to be similar to what happens when we move the graph of, say, x squared to the graph of x squared plus 4. But here's the example I want us to look at. Sketch the graph of f of x equals square root of x plus 4. Now, to start, I need to make sure that you and I are on the same page here. Notice that we have not replaced the x by x plus 4 here. That's a very different thing. In the previous example, I actually just replaced the x by x minus 3. But in this case, I have not replaced the x by x plus 4. What I've actually done is just added a 4 to the outside of the square root symbol. So here I'm adding 4 to the whole function square root of x. And when you add a number like 4 to a function like square root of x, it means that the graph of square root of x plus 4 is identical to the graph of square root of x, except we take that original graph of square root of x and we move it up 4 units. Not left or right, we actually shift it upwards by 4 units. So, the graph of the square root of x started at the origin and moved up to the right. The graph of square root of x plus 4 now starts at the point 0, 4. It's been shifted up 4 units, and now it will again make that nice upward motion from 0, 4 into the first quadrant. Notice that there are no other changes to the graph except for this nice shifting from the origin, basically, up to the point 0, 4. Now, let's put these ideas together and try to look at a slightly more complicated graph that still involves a function with a radical symbol in it. So here's the function I want us to look at now. Sketch the graph of f of x equals square root of x minus 2 plus 6. Okay? Now, notice that this function has a square root in it, except now we've gone from the square root of x function as a starting point, and we've done 2 things to that. We started with the square root of x, and we replaced the x by x minus 2 to get us to square root of x minus 2. That's one thing that we did. And then we also tacked on a plus 6 to the whole function. See how that plus 6 is hanging out outside of the square root symbol. That means that the graph of this new function that we want to study is the same as the graph of the square root of x, except that 2 new things have happened. First of all, by replacing the x by x minus 2, our new graph takes the graph of square root of x and shifts it right 2 units. That's what the change from x to x minus 2 does. So now I've started with the square root of x, which comes right out of the origin, and shifted it over 2 units. Then the plus 6 takes that graph and shifts it up 6 units. And that's exactly what the function rule tells us that we did, in fact. So my graph should be now at the point 2, 6 as its sort of starting point, And then from 2 comma 6, it takes off and has the same shape as before and goes up into the first quadrant, just as the other graphs have done. It's pretty cool, actually. Rather than plotting a whole bunch of points and trying to draw all this stuff, we're able to think critically about what these graphs look like. And I think the idea of doing this in 2 steps is really nice. Now, we focus quite a bit of attention on the graph of the square root function and a few of its cousins, right? Square root of x minus 2 or square root of x minus 2 plus 6, for example. But there's much more to the family of radical functions than the square root function. So now I'd like us to move to another example that compares the graph of the square root function to the graph of a few other functions. So here's the example. On the same set of axes, I'd like us to plot f of x equals square root of x and g of x equals the 4th root of x. Okay, to start, we know how to graph f of x, because that's the square root of x, so we can easily do that quickly. We've already talked about that today. What about the graph of g of x? Well, one thing to notice is that the domain of g of x is the same as the domain of f of x. It's the set of non-negative real numbers. And that's because you can't plug in a negative number into the 4th root of x function. Okay? So both of these functions have the same domain. Next, let's plot some points just to see where this graph is going to go. So we're looking now at the g function, and I'm going to plug in now some, again, very specially chosen values just to see what we have. So first I want to do g of 0, which is the 4th root of 0, which is 0, so that's fine. That tells me this function starts at the origin. G of 1, which is the 4th root of 1, is equal to 1. And now, again, I'm going to pick my values of x carefully. So let's try 16 next, because g of 16, which is the 4th root of 16, is 2. So now I know that I can plot the point 16, comma 2. Let's do a few others. G of 81 is the 4th root of 81, which of course is 3, because 3 to the 4th is 81. And lastly, g of 256, which is the 4th root of 256, is equal to 4. So I now have 5 points on the graph of g that I can plot. 0, 0, 1, 1, 16, 2, 81, 3, and 256, comma 4. Those are all on the graph of g. By the way, 256 in the x direction and just 4 measly values up on the y direction, this function is definitely not growing very quickly as the x values get large. Now, let's compare these two graphs, the graph of f and the graph of g. Notice that both of them go through the points 0, 0 and 1, 1. So these are 2 places where the graphs intersect. That's one thing we can say. What else can we say? Well, we see that one of the graphs is flatter than the other, at least as the values of x get large and above 1. And if you look at those 2 graphs for just a moment, you can see this, that the one graph seems to be flatter than the other. Which one is it? Well, the flatter one, or lower one, if you will, after x is bigger than 1, is the 4th root function. But don't be fooled, it doesn't go flat like a straight line. The graph of g of x equals the 4th root of x also goes to plus infinity in the y direction. It's just that it does it even slower than the graph of the square root of x, if you can imagine that. Now, there's something else you should notice. Notice in the little part between x equals 0 and x equals 1, the graph of the 4th root of x, or g of x, is actually above the graph of the square root of x. Remember, these 2 graphs have exactly 2 intersection points, 0, 0 and 1, 1. And those dictate that one of the graphs has to be above the other for a while, and then the roles of who's going to be above and below will switch. And that's exactly what we see here. So between x equals 0 and 1, the 4th root of x is actually the one that's above, and then at x equals 1, the roles of which one will be above and which will be below actually are reversed. And the square root of x function is actually the one above. Now, let me make one last comment before I close out this example. How would you actually draw graphs of, say, x to the 1/6 or x to the 1/8 and compare those to the graphs of square root of x, which is x to the 1/2, and the fourth root of x, x to the 1/4. Well, the graph of x to the 1/6, as well as the graph of x to the 1/8, will also start at the origin, and they will also go through the point 1, 1. So they would all have these two intersection points, and believe it or not, they're all going to have this same sort of swooping shape in the first quadrant. So what could we then say about these four graphs in comparison to one another? Well, for values of x from 1 to infinity, the graph of any one of these kinds of power functions that has a smaller fractional power would be below the graph of any function with a larger fractional power. That's in the case from x equals 1 to x equals infinity. So you would almost see this cascading effect, if you will, if you drew several copies of these graphs. One for x to the 1/2, one for x to the 1/4, x to the 1/6, x to the 1/8, and so on the same set of axes. So there's a nice, if you will, shape to this family of graphs, and we can tell exactly which ones will be above which other ones. Okay, let's move to a different example now, and this example is very different because the power we're looking at has an odd denominator. Did you notice that all the graphs we just looked at were of functions that were of the form x to the 1 over an even power? So like x to the 1/2 or x to the 1/4, x to the 1/6, and so on. In this example now, I'd like to sketch the graph of f of x equals x to the 1/3, and 3 is odd, so this is going to look very different. Now, how is it going to look different? Well, one of the reasons it's going to be very different is because the domain of this function is actually very, very different from the domain of the other functions, and it's all because that denominator of the fractional power is now odd. Notice that the domain of x to the 1/3 is actually now all real numbers. And the reason for that is, even in the function f of x to the 1/3, I'm allowed to plug in negative values for x. So, for example, in this function, I can plug -8 into the function, and -8 raised to the 1/3 makes sense. And in fact, it just equals -2. So here you have an example where this function's domain is allowed to have negative values, whereas in all of the functions I was talking about earlier today, the domains had to start at 0 and go to plus infinity. So in this case, the domain is the set of all real numbers, and that's going to mean that the graph is going to stretch across the whole xy plane, if you will, not just be in the right-hand side of the plane. So that's a very big difference with this example compared to the others. Now, with that said, what's going to happen to this graph compared to the others? Well, like functions like the square root of x and the fourth root of x, the graph of f of x equals x to the 1/3 does go through the origin, right? Because 0 to the 1/3 is 0. And it's the only x-intercept for this graph. So we could plot that point if we wanted. Notice also that this function goes through the point 1, 1, just like the others, because 1 to the 1/3 is 1. So we could plot that point as well. And now let me suggest we plot a few more just to get a feeling for what the graph looks like. We know f of 0 is 0. We should have already plotted that point. And f of 1 is 1. Again, we should have that one plotted. Notice that f of 8 equals 2. We did that a moment ago. 8 to the 1/3 equals 2. Since 27 to the 1/3 equals 3, I know that f of 27 equals 3, which means I now have the point 27, 3 on my graph. And lastly, for now, f of 64 is 4 because the third root of 64 is 4. Now, I can also include negative values for x. So let's see what's happening as we go through some negative values for x. Well, first of all, f of -1 is now equal to -1. So that's a nice choice. I know that I can plug in the -1 for x and get -1 back for y. F of -8 is -2, and f of -27 is -3. And lastly, f of -64 is equal to -4 because -4 raised to the third power is equal to 64. So now I have a whole bunch of points that I can actually plot. And if you just plot each one of those on a piece of graph paper very carefully, you'll see that the graph looks something like this. Now, that's really nice, and I want you to notice that it's got a piece on the right-hand side of the plane, if you will, just like the square root of x did. But notice that it has something on the left-hand side as well, which looks like the mirror image of the right-hand side, except now it's over on the left-hand side of the xy plane. So, thanks to the fact that the domain of this function is a set of all real numbers, I now see that the graph actually goes in both directions, not just in one. Now, let me make one additional comment here. I want you to notice that the graph actually looks like it goes vertical, so to speak, as it goes through the origin. It turns out that it really does go vertical, at least from the point of view of differential calculus. Now, I can't really speak much more about this in this course, because we're not a calculus course, and because we need a lot of other tools in order to prove, or to at least explain, why this graph appears to be going vertical. But just let me say this. When you get to calculus, and my hope is that that's your plan as well, you'll be able to see more fully why this graph appears to go vertical as it goes through the origin. Now, let's look at another graphic example of a rational power function, this time where the denominator of the power is odd, but the numerator is actually even. So here's a new twist. Sketch the graph of f of x equals x to the 2/3 power. Okay, now we have to pause and think for a moment about several things before we just sort of jump in and start drawing this graph. First, we know from our previous work on these kinds of functions that this f of x could be written as x to the 1/3 squared. We saw this with our laws of exponents. So that means that we could quickly calculate several values of this function if we wanted. Okay? So for example, we know that f of 0 is obviously still 0, and f of 1 is still equal to 1. But now what is f of 8? So f of 8 is going to be 8 to the 2/3, which is the same as 8 to the 1/3 squared. But that's the same as 2 squared, which is 4. So f of 8 is equal to 4, which means that the point 8, 4 is on this graph. Let's do one more of these. F of 27 would be 27 to the 2/3, which is the same as 27 to the 1/3 squared, which is 3 squared, which is 9. So that gives me another point on this graph, 27, 9. Now also notice that negative values of x are allowed here. And again, they're allowed because the denominator is odd. The fact of whether a negative value is going to be in the domain of one of these functions is all about the denominator of the power, not about the numerator. And when you plot a few points, you can see what kind of y values are going to happen. Plug in -1 for x, and f of -1 then is -1 to the 2/3, which is -1 to the 1/3 squared, which is actually -1 squared, which is +1. So now I've got the point -1, +1 on my graph. Let's just do one more of these quickly. F of -8 would be -8 to the 2/3, which would be -8 to the 1/3 squared, which would be -2 squared, which would be +4, not -4, it would be +4. And now we see a difference between output values of this function, x to the 2/3, and output values of something like x to the 1/3. When we plug in negative values of x for this function, we get positive values back for the y's. And that's because of the 2 in the numerator of the power. It's squaring all of the outputs, if you will, and that means all the negative signs are being canceled. So what does the graph look like? Well, the right-hand side has this sort of similar shape. Remember, it's starting at the origin. If I start at that origin, the right-hand side has a similar shape to all the other graphs we've seen in this lesson. But now the left-hand side is slightly different. Rather than going below the x-axis, as it did for x to the 1/3, now at the origin, the left-hand side actually also goes upwards into that quadrant. And because of that, you get a graph that looks a little bit like what some children draw as a seagull or a bird in elementary school. Starting at the origin, it sort of goes out in both directions in an upward fashion rather than one side going up and the other side going down. Now, before I close this lesson, let me make one comment about graphs of inverse functions. So for our purposes, let me just say that inverse functions are functions which undo one another, so to speak. So for example, x cubed and x to the 1/3 are inverse functions because if you plug in 2 into x cubed, you'll get 8. And if you plug in 8 into x to the 1/3, you get the 2 back. So one does what the other one doesn't do. They sort of undo one another. Now, what should you notice then about the graphs of these two functions when they are inverses? Well, it turns out that their graphs are symmetric to one another, and they're symmetric to one another about the line y equals x. So if you were to graph, for example, the graph of y equals x cubed and the graph of y equals x to the 1/3 on the same set of axes, and then draw the line y equals x on that same set of axes as well, you would see that the graph of x cubed and the graph of x to the 1/3 are mirror images of one another about the line y equals x. I could say more about this here, but we need to talk more about things like the composition of two inverse functions and so on. For now, let me just stop here and simply say that if you want to talk more about inverse functions, you should definitely move forward into pre-calculus and calculus, where these kinds of things will be discussed in more detail. Well, we've talked about these graphs of radical functions today and what their domains look like and so on. And I hope that you've been able to see these cool ideas about graphs of these very special functions.